Welcome to the Deep Dive, your shortcut to being well-informed. Today we're taking a deep dive into, well, a really fascinating intersection. We're talking artificial intelligence and quantum physics. We're exploring an intriguing essay by Jorgo Schneepat titled Quantum Text Classification KI Drift Quantum Power, which basically translates to Quantum Text Classification AI meets Quantum Power. Our mission today, it's really to unpack how this mind-bending power of quantum computing is starting to shake things up. Specifically, how it might revolutionize something as fundamental as text classification. You know, how AI understands and sorts written language. Think of this as your fast track to understanding a future that's, well, it's already starting to take shape. Hopefully with some surprising facts and maybe a few aha moments for you along the way.
Absolutely. What's truly captivating here is seeing these two fields, quantum mechanics and machine learning, which seems so different, actually converging. And this synergy, it's aimed squarely at tackling some of the biggest challenges we face in AI right now. Mr. Schneepat's work really highlights this. Text classification isn't just some, niche academic thing. It's a cornerstone. It affects everything from your spam filter right up to sophisticated sentiment analysis that tries to figure out public opinion. So at its heart, text classification is just the automatic assignment of text documents to categories we've already defined. It's a task that is absolutely crucial for making any sense of the, frankly, vast amounts of text data we're all generating every single day.
Okay, yeah, let's unpack that a bit more. Before we jump into the whole quantum angle, let's make sure we're all clear on text classification itself. What exactly are we talking about and why is it such a big deal in AI today?
Right. So text classification is absolutely fundamental to natural language processing, NLP. It's kind of the silent engine running behind so much of what you interact with online. Think about spam detection in your email, or how social media sites try to analyze customer feelings, even how scientific papers get categorized for researchers, or how automated translation gets better over time. Essentially, it's about teaching computers to read and sort information like humans do, just way faster and on a massive scale. Now, historically, we've used methods like naive Bayes, support vector machines, SVMs, you often hear them called. And more recently, these really sophisticated neural networks like the big transformer models, BERT-style models, these classical methods, they're powerful, no doubt. But their success really depends on complex math, optimization, running on just enormous amounts of data. And this is where it starts to get tricky. Classical methods really hit roadblocks. They struggle with the sheer size and complexity of the data we have now. For instance, when you turn text into numbers, things like word embeddings, the capture, meaning these models can create mathematical spaces, vector spaces that just grow exponentially huge. This means training takes forever, and they can easily start overfitting. That means they get too good at the specific data they were trained on, and then they fail when they see new text. It's like trying to sort a constantly expanding library with millions of categories.
Okay, so classical computing is hitting a wall with this data explosion. What does that mean for us then? Well, these limits seem to be exactly where quantum computing comes into the picture. Now, for those of us, myself included perhaps, whose quantum physics is a bit rusty, can you give us the absolute essentials? What makes a quantum computer so different, so powerful?
Sure thing. So unlike a classical bit, which is always definitely 0 or 1, right? A quantum bit, a qubit, can be in what's called superposition. It can be both 0 and 1 at the same time. The usual analogy is a spinning coin. It's neither heads nor tails until it lands, until you measure it. This basic property allows for parallel computations on a scale that's just impossible, classically. Then you have entanglement. This is where 2 or more qubits become linked in this really deep way. If you measure one, you instantly know something about the other, no matter how far apart they are. It's weird, but powerful. And finally, there's quantum interference. This is used cleverly to make the correct computational path stronger and cancel out the incorrect ones, sort of guiding the calculation to the right answer. So think about it. A classical computer works step by step, sequentially. A quantum computer, using superposition, can explore many possibilities at once, in parallel, and it uses entanglement to manage correlations between these qubits really efficiently. This combination offers the potential for exponential speedups, but importantly, only for certain kinds of problems. And that's why you hear so much about algorithms like Shor's algorithm.
For factoring large numbers, right? Breaking encryption.
Exactly. And Grover's algorithm, which gives a quadratic speedup for searching unstructured data, they show a fundamentally different kind of computing power.
Okay, I think I follow. Superposition, entanglement, interference, these unique quantum tools. But how does all that abstract physics actually help with something practical like sorting through mountains of text? Why is quantum computing specifically interesting for text classification?
Yeah, this is where it gets really fascinating, I think. Remember how we said text data, when you represent it numerically, often lives in these incredibly high-dimensional spaces? Classical computers just bog down trying to handle that complexity. Quantum computers, though, because of that inherent parallelism from qubits, they can explore and process these huge vector spaces much, much more efficiently. It's a potential game changer for how we deal with complex text representations, like those word embeddings we mentioned. It's not just about speed, it's about handling more complexity simultaneously. And there's more. Those quantum phenomena, entanglement and interference, they might allow quantum algorithms to find subtle hidden patterns in data that classical methods just miss. Think of it like seeing deeper connections, maybe nuanced relationships between words or concepts in language that are just too hard for classical sequential algorithms to spot. Plus, a lot of machine learning, especially deep learning, relies heavily on matrix math, huge matrix operations. There are quantum algorithms, like the HHL algorithm, designed to solve systems of linear equations potentially much faster than classical ones. Since those equations are core to many machine learning tasks, this could dramatically speed up the training and operation of many NLP models. It could make analyses feasible that are just too slow today.
Wow, okay. That really does sound like a completely new toolkit for seeing and processing language. And you're saying this isn't just pie in the sky theory. Researchers, like Yergo Schneepat discusses, are actually building specific quantum algorithms for this. What are some of the key approaches they're trying out right now?
Definitely. One prominent approach is the variational quantum classifier, or VQC. It's a hybrid approach, which is quite common right now. It mixes classical computing with a quantum circuit. So you encode the text data into quantum states, and then you have a quantum neural network, basically a quantum circuit with adjustable settings that learns to classify the data. The classical computer helps optimize those settings. It's kind of like having a classical brain guiding this very powerful quantum intuition. Then there are quantum-enhanced kernel methods, QKE.
Okay, kernels, like in support vector machines.
Exactly. Classical kernel methods work by cleverly measuring similarity between data points, sometimes in very high dimensions, without actually having to compute coordinates there. It's a mathematical trick. QKE aims to use quantum computers to calculate these similarity measures, these inner products, potentially even more efficiently in even higher dimensional spaces. This could lead to exponential speedups and maybe better generalization, meaning the model works better on new data. The key idea is that quantum computing might let us explore a much richer meaning space for language, finding connections classical methods can't computationally reach. We also see work on quantum Boltzmann machines, QBMs. These are quantum versions of classical Boltzmann machines, which are used for learning probabilities. QBMs might be able to model more complex probability distributions, maybe process large texts faster. This could be really useful for understanding complex relationships between words or topics in documents. And of course, Grover's algorithm. We talked about its search speedup.
The square root of n steps thing?
All right, so you can adapt that. Imagine searching a massive database of documents for something specific. Grover's could make that much faster. Or using it for things like named entity recognition, finding specific names, places, organizations in text. Again, the potential insight is that speed up for finding the needle in an ever-growing haystack.
It genuinely sounds like quantum offers this whole new angle on NLP, finding patterns, speeding up searches. It's powerful stuff. But okay, let's get real for a second. We know quantum computing is still pretty early days. That journey from theory to practice is usually long. So how far along are we? What does practical implementation look like right now? How are people actually testing these ideas?
Yeah, that's the crucial reality check. Right now, researchers mainly use software frameworks. You hear names like IBM's Qiskit, Google's Cirq, Xanadu's PennyLane. These are mostly open source tools that let you design quantum circuits, simulate them, and sometimes run them on actual quantum hardware that's available, usually through the cloud. PennyLane, for example, is really geared towards that hybrid quantum classical machine learning we talked about. And that hybrid word is key. Most current approaches are hybrid. You use classical computers for what they're good at, maybe cleaning the text data, doing some initial processing. Then you hand off the really computationally tough parts, like maybe extracting complex features or the final classification step, to a quantum processor.
So they work together.
Exactly. Playing to each system's strengths. Now, most experiments today, they're still run on quantum simulators on classical computers. Simulators let you test the algorithms perfectly, without the noise and errors of real quantum hardware. And the early results you see, usually on small, controlled data sets, they often look promising, and sometimes competitive with classical methods. But scaling up to handle the huge text datasets we use in real-world NLP, that's still a major, major hurdle. We're deep in what people call the NISQ era. Noisy intermediate-scale quantum, meaning the quantum computers we have are still relatively small in terms of qubit count, and they're quite prone to errors or noise. Which brings us neatly to the biggest challenges. Real quantum computers are very sensitive. Qubits lose their quantum state really easily. It's called decoherence. Just interacting with their environment throws them off. There are also errors in performing quantum operations, the gates, and errors in reading out the results. And fundamentally, we just don't have enough stable, high-quality qubits yet. Remember that Deland 1024-dimensional word embedding example? That needs at least 10 perfectly functioning qubits. Real NLP models use dimensions in the hundreds of thousands or more. We need way more qubits than we have now, and they need to be much more reliable.
Okay, so the vision is exciting, the potential seems huge, but the hardware road is definitely still under construction. Lots of challenges. But despite those hurdles, the pull towards quantum is strong. Looking ahead, what advances in hardware and algorithms do we realistically expect? And if, or maybe when, these challenges are overcome, what could the real-world impact of quantum text classification actually look like?
Well, progress on the hardware front is actually moving quite fast, considering the difficulty. We're seeing continuous improvements in different qubit technologies. Superconducting qubits, like IBM and Google use, are fast but need intense cooling. Ion traps, used by companies like IonQ and Honeywell, have qubits that last longer, more coherent, and are very precise, but maybe a bit slower. Then there are photonic approaches, using light, which could potentially run at room temperature. That's another avenue. The push is always for more qubits, better ways to connect them, and reducing that error noise. All absolutely critical for NLP. On the algorithm side, we expect to see new quantum machine learning models emerge, maybe one specifically designed for language's complexities. We'll likely see better quantum kernel methods for handling those massive meaning spaces, refinements to things like quantum Boltzmann machines. A really hot area is figuring out how to combine quantum algorithms with the best classical models we have, like those big transformer architectures, GPT, and so on. Maybe quantum can speed up the bottlenecks in those models, like the huge matrix calculations they do for their attention mechanisms, how they weigh word importance.
So augmenting the best of classical AI.
Precisely, making it even more powerful. And if this pans out, the impact could be massive across industries. Imagine search engines that don't just find keywords but understand context and nuance across billions of documents instantly. Think about automated translation becoming much more fluid and accurate. Or analyzing complex legal documents or medical research papers incredibly quickly, finding connections humans might miss for years. It's really about giving AI a deeper, faster grasp of human language.
That's truly remarkable to think about. It suggests a future where AI doesn't just process language faster, but maybe understands it in a fundamentally different, richer way. So, thinking beyond just speed, what specific kind of insights about language itself might quantum text classification uniquely uncover? Things that classical AI by its nature might just be blind to.
Wow, what a fascinating journey into the world of quantum text classification. We've really seen how Jürgen Schneppat's essay sketches out this potential future where these pretty mind-bending quantum principles could fundamentally change how AI handles our language.
Indeed. And while we are definitely still navigating this NISQ era, the noisy intermediate-scale quantum phase, the potential is definitely there. Potential for exponential speed-ups, finding new kinds of patterns in this high-dimensional data, it's profound. And that synergy, that collaboration between classical AI and quantum computing, especially using hybrid models, that really seems like the key to unlocking advanced NLP applications sooner rather than later.
The research is incredibly exciting to follow, that's for sure. The future of how we classify text really might be quantum mechanical. We absolutely recommend digging deeper into this area if it sparked your interest and checking out Jürgen Schneppat's work. That's all the time we have for this deep dive. Thank you so much for joining us on this exploration. You can find more information about Jürgen Schneppat's work and related topics at schneppat.de. That's schneppa.de. Until next time, keep digging, keep questioning, and keep learning.